Let me just start the recording. Can you just type something to let me know that you can hear me before we get started? Okay, thank you, Malawi. Okay, so let me get started over here. So today is our last chapter in the course. It relates a little bit to the end of what we covered in the last chapter about package coupling and cohesion principles. Is in the sense that there is some math. There's quite a bit of math involved in this course, but it's not difficult math. It's actually very, very simple math, but it's the first time in this course that we use numerics and we use math in order to guide our design efforts. All right. So yeah, this chapter is about measurement and metrics in design. Although the chapter says measurements and metrics in design, measurements and metrics, they apply to every aspect of the software development lifecycle, all the different processes and all the different products as well. Okay, not just the final product, not just the source code, not just the design, but even the requirements document, the testing, artifacts, and so on. All right, so we're going to be looking at this this chapter to define software metrics and measurement and understand the different types of metrics, understand the principles of measurement and process, and to describe some examples of design metrics. Okay, so the word metric that I keep throwing around, this is a concept that is important for us to that defines some sort of an attribute, a very important attribute about our software. Okay, whether the software product, the process, or resource. Okay, for example, one metric, for example, about ice cream is temperature, because temperature would be a quality indicator, because a high temperature ice cream, that's not really good. But if the temperature was low, that would be an indication of that ice cream being of good quality. All right, there could be other metrics that are completely irrelevant to the ice cream. For example, GPA, your GPA, for example, right? That has absolutely no relevance to that ice cream, and it doesn't say anything with respect to how good or bad this ice cream is. Okay, let's take another example. Okay, let's talk about you as a student. All right, we look at the GPA as a metric of how well you are performing academically. All right, now how well you are playing football or how well you play PlayStation, that's a metric, but that's not of you as a student. Okay, because that metric describes nothing with respect to how good or bad you are as a student. Okay, it doesn't indicate anything about your academic performance. A measure is the actual number that we get. So with a GPA, it'll be a 3.5. With temperature, it'll be minus 20 degrees. All right. Speed, agility, and so on. You see, for example, in football teams on PlayStation, this is the actual number, an actual instance of a number of that metric. And then measurement is the act of trying to go ahead and get that measure. Okay, so we do the measurement in order to retrieve and obtain a measure. So dipping the thermometer into water or dipping the thermometer into the ice cream to get its temperature, this is the act of measurement. Okay, you read the temperature, for example, says minus 10 degrees Celsius, that's the measure. Okay, and what are we measuring? Temperature. So temperature, right, is an indicator of how good or bad our ice cream is. So temperature is an ice cream metric. Okay, now when it comes to software, there is three aspects that we gather metrics about, because at the end of the day, software is about creating a product. Okay, but in order to create a product, there's got to be a process. There's got to be a process that leads to the creation of the product. This process requires some resources. All right, now each one of these three aspects, the resources, the process, and the product, each one of them can have metrics. Okay, so for example, the resources that I'm using in the process is, for example, the people that I'm using. Okay, how much money do I have? What is the education level of my programmers? All right, how much office space do I have? How much licenses, software licenses do I have that will aid me into doing the software development? So these are resources that I'm using throughout my process to create my product. The process itself, could be things with respect to testing, design, requirements. Okay, so the process could be things like how much time did I spend on requirements, how much time did I spend on design, how many people did I use, how many bug reports do I have, okay, how many of them are severe, how many of them are intermediate. Okay, these are numbers describing to me the progress, evaluation of the actual process that leads to the development of the product. Now that we do have the product itself, there is some metrics about the product itself. For example, how many lines of code does it have? Okay, for example, how many use cases do we have? How many classes do we have? And so on and so forth. These are actually describing the product that we've actually created. All right. So any questions about what we've covered so far in those first few slides? Let me just make sure I get this check. Oops. Why am I not seeing the actual shows? Any questions? Okay, good. All right. Type. Let me just erase this. All right, so another aspect that we can categorize our metrics with is whether these metrics are static or dynamic. Okay, now static metrics, these are metrics about my product, my software, as it is in a static mode, so it's not running. Okay, things like how many classes do I have, how many lines of code do I have, how many methods per class do I have, and so on. Okay, these are the sort of metrics that are good to help me assess things like complexity, understandability, and maintainability. Okay, now these are things I can only figure out while the software is at a pause state, it's not running, as an idle state, and I look at the artifact, I look at the source code. Okay, now there's other things that I could not figure out, I would never be able to figure out while the software is not running. I have to get it to run. So these are called dynamic metrics. And these are metrics that I gather, metrics that I measure while the software is running. For example, how much CPU is it eating? How much memory is it eating? All right. What is the processing time? What is the transaction throughput? Which tells me my efficiency. How many times does it fail? The mean time between failures, that tells me my reliability. Okay, and these are the sort of metrics that would explain to me, for example, what parts of my software and what functionality that actually causes bottlenecks. Okay, so that's the big parts of performance engineering. It relies heavily on us collecting what we call dynamic metrics. All right, the advantages of using software metrics. All right, in general, you cannot control what you cannot measure. All right, same like in any aspect in life. Okay, it's hard to control your weight if you cannot measure it and you don't see a progress. You don't really know if you're actually doing well or not. Okay, despite people's compliments. Same thing with ice cream. Same thing with your academic performance. You have to have some sort of a measure in order to know whether I should be doing better or whether I'm doing okay. All right, so metrics, they give us number, they quantitatively define success or failure. Not just success or failure, but actually even the degree of success or failure. So did we just pass or not pass? This is one thing, but if we did pass, how well did we pass? Okay, getting an A is different than getting a D. And the same applies again to the product, the process, and it says here the people, but it means actually the resources. Okay. Now, once I have those numbers, I can make some meaningful decisions with it. Okay. So I can look at those numbers and identify trends, all right, the way the software is heading. Okay. Similarly, as the people do in marketing, they look at their numbers and they see where is the market going. And with it, I can then make decisions to affect those trends or capitalize on those trends. All right. And then I go back again, I do more measurements to see how well and the degree of success did my decisions have. Okay. Obviously, it could be degree of success, or it could be a failure or a degree of failure. In general, if you can't see a number, okay, if you can't see a number, you have no idea where you're heading. All right. So you cannot control what you cannot measure. Now, the disadvantage of metrics is that if it's misused or collected in a wrong way, it could be harmful. All right. So you apply this to anything. Okay, you're reading the temperature, but if you're getting the wrong temperature, then you're acting on the wrong numbers and the wrong data. That's obviously very, very harmful. If you get the right data, but based on it, you actually misuse it, that's also very, very harmful. Okay. What if I get the data right and I do some faulty analysis, some statistical analysis that is not correct? It makes those metrics useless. Here's a classic example. Let's just say you have an island, 10 people on those island. One of them has $1,000,000 reals or $1,000,000, and the other 9 got $1 real each or $1 each. You would say that the average, if you do the math, the average is approximately 100,000 per person. Okay, but this computation is completely meaningless, not to mention that it doesn't actually represent anybody on that island. All right, that 100,000, there's one person who has a lot more than 100,000, and there's 9 people who's got a lot less than 100,000. So it doesn't really make sense when we say something like, what is the average? Say, for example, the average is a B in a classroom. That's usually because we're expecting that there's a majority of the students who actually got a B, and a few of them who got an A, and a few who got a C or a D. Okay. For metrics to be useful, metrics must be gathered systematically. All right. Now, if I want to know the average temperature in Riyadh, I have to get my measurements systematically once a month. Okay. If I want to know the average temperature throughout the year, doesn't make sense that I go get 6 measurements in July and 1 in November. All right. It's not gonna make sense. Preferably, if there's an automated tool that can do that for us, it helps us achieve this systematic approach to our metrics collection, our measurements, then this would be definitely very, very useful if it's available, if it's feasible. It's definitely not an easy task. The thing about metrics is that they're interrelated, okay? Some of them have what we call a positive correlation with each other. So you improve one, it improves the other one. Some of them have a negative correlation. Okay, so you improve one, all right, and then the other metrics get reduced. Okay, so if you focus, for example, too much on offense, then you're reducing your ability to play defense. All right, and so on and so forth. Metrics need to be validated in order to be used, which is again not a trivial task. Okay. So if I ask you what's the temperature outside, and you said, for example, this is 22 degrees Celsius, that's a valid number. It's not necessarily the correct number, but at least it's a valid number. But if I ask you what's the temperature outside, and you said the temperature outside is an F, that's invalid. Now that's pretty easy. It's pretty obvious that F doesn't even count as a temperature, let alone figuring out if it's the accurate measurement of the temperature. All right. So in other situation, receiving a number that is not even valid may itself not be easy to recognize that it is invalid. Okay, so going back again to this temperature thing, and I asked what's the temperature outside, you said 2000 degrees Celsius. Obviously that is invalid for us because 2000 degrees Celsius, we will all be dead by now. Everything would have melted and evaporated probably. But in other situations, you don't really have a range. You don't really have an idea of what is the number you should be getting. Should it be 1? Should it be 10? Or should it be 10 million? You really have no way to say. So if you do get a number that is way off, sometimes it's actually not trivial to know and to see how way off, that this number is actually way off and invalid. Now, there is some principles to measurements that should be, first of all, the objective of the measurement needs to be there, all right, before we begin. So when we said something about the ice cream, okay, or even the GPA, let's talk about GPA, okay? The GPA, and the reason we do a measure is because it does establish for me, that you have a mastery of the concept that you've been taught in class, okay? Why is it that we don't really factor in how good or bad you play football? Is because it's not actually an indication of your academic performance, okay? So when I say, all right, I'm going to give you a quiz and I'm going to score that quiz, okay, there is a concept here, there's a reason, all right, because that quiz and this measurement indicates to me how well or not well are you actually understanding the concept that I'm teaching, right? But I, the professor, would not go and judge your skill level in playing football because, from my perspective, it has absolutely no influence and no indication of your academic performance. Each technical metric should be defined in an ambiguous manner, okay? So, things like temperature or GPA, all right, or the A grade or a B grade, okay? We have percentages. We have 95 to 100, that's an A, right? 90 to 94, that's an A minus. We don't just say roughly around 90, then you give an A, or roughly around 95, you give an an A plus. It doesn't work like that. It has to be defined. Okay, it has to be defined in an unambiguous manner. Okay, if you say lines of code, what do you mean a line? Okay, is it a statement? What if I have an if statement that is across multiple lines? Does all of those count as a line, or is the whole condition counts as one line? All right. If I say, for example, the number of characters in a piece of source code, does that include tabs? Does that include white spaces or not? So it has to be defined in an unambiguous manner. Metrics should be derived based on theory. We already explained that before. Metrics should be tailored to best accommodate specific products and processes. So for example, we know there is two development life cycles, like for example, the waterfall method and the agile method. And the agile method uses a completely different way of doing things and developing software than the waterfall approach. So it doesn't make sense that the same metrics that I'm using for the waterfall is the same one that I apply and I judge the progress and the success of a software development project that is using agile. Okay, so if I'm using agile, gotta use the agile metrics. If I'm using waterfall, then I have to use the waterfall metrics. All right. And again, let me pause here for a second, see if you guys have questions. Everything clear so far? All right, thank you, Rada. All right, moving on. So we have a process for measurement, first of which it's 5 steps. The most obvious step is you gotta formulate the metric, okay? This is where the science comes in. This is where the research comes in, okay? Some people somewhere are gonna realize that the student's ability to understand design concepts, that is an indication of how well they are as a software engineer. All right, that has to be formulated, and then the numbers got to be formulated. Okay, so how good is good and how bad is bad? Okay, so this is a formulation, it's the derivation of software measures and metrics appropriate for the representation of the software that is being used. All right, so I have this software. I say that, for example, the number of lines of code, that's an indication of obviously immediately how big that software is, but how big that software is also an indication of its complexity, and its complexity affects my understandability, and my understandability affects my maintenance and my reusability. All right, so anyway, so step number one is formulation. I gotta formulate it. I gotta decide what is the metric. What does the numbers mean? Okay, so 95 to 100 is good, and as a mark for your exam. Getting 30% is not good. Okay, but I gotta define those, and I gotta define them in an unambiguous manner. Now, next up is the measurements. Going ahead and collect it. Okay, so collection, like we said before, we're better off if that collection is periodic, systematic, and even better if it's done by a software tool, because it reduces the human error. It makes sure that the timing is correct. Software usually doesn't forget. Okay. After we've collected all this amount of information, then we do the statistical analysis with it. Okay, so the analysis. Now, the analysis means breaking down something for the purpose of understanding it. Okay, and when we do statistical analysis, we are crunching numbers together, again, for the purpose of understanding it. Okay, so analysis, for example, could be, I want to calculate the average of a class. Right? Again, I got to be very careful, because if it's a bell curve, then that average number is good. It's indicative of the general popularity that I have in my classroom. But if it was not a bell curve, but rather a U curve, in other words, most students are either A or D, then that means that the average is still going to be a B or a B minus. But that B minus doesn't represent a lot of students. Okay, so we got to do the number crunching, but we got to be careful that this number crunching is actually producing numbers that is meaningful. Now that I get these numbers that I've done from the crunching, I got to interpret it. Okay, so I look at it, I say, okay, so the average is 75. All right, good. No further action is needed. Okay, or if I say, well, the average is 50. Uh-oh, that's not good. The majority of my students are doing 50. That means roughly half of them have failed. Then I gotta take action. Okay, I gotta understand why they're not performing well. Gotta maybe change my method of teaching. Gotta change my the exercise that I'm giving, and so on. If the average is 95, all right, maybe the exams are too easy. All right, or maybe the students do actually understand very well. All right, so anyway, I got to make an interpretation. This interpretation would lead to the last step, which is the feedback and taking action based on my interpretation. Okay, so when I looked at the number and it said 75, maybe my feedback is nothing. Just keep at it. You're doing good. If it was 95, maybe the course is too easy. Maybe the students can handle more and they're up to the challenge. If it's 50, maybe they're not up to the challenge. There's something wrong. Maybe I should add more exercises, give more help sessions, or make the exams a little bit easier, and so on. I got to understand why. So there's a feedback loop that's going on over here. Now, to the interesting part of this chapter, which is some examples of metrics. At the architectural level, for example, we have something called the number of classes and interface. And this is the number of concrete and abstract classes in a package, is an indicator of its extensibility of the package. And again, we've looked at this as the abstraction metric that we looked at towards the end of the last chapter. And basically, the more something is abstract, the more it is that I can use it and extend it. Okay. Now, remember, um, all the design pattern class diagrams that we created. Okay. We had an abstract class and we kept extending it with subclasses. Okay. It's easy to extend that abstract class with concrete subclasses. But if you take one of these concrete subclasses and you want to create subclasses of that, it is not as easy. Okay. So the number of class and interfaces, the number of concrete and abstract classes in the package is an indicator of if it's the extensibility of the package. The next two we've already seen before, and these are the afferent coupling and the efferent coupling, and those are the ones that let me judge the stability. Remember the ones with the class diagram, sorry, with a class, and we see how many incoming arrows and the outgoing arrows. So we've already seen this before, and we were able to calculate the stability metric. Okay. Now, at the architectural level, looking at a package. Okay, this is new for us now. We want to judge the level of cohesion. Okay, so remember we said we want to have a high level of cohesion and a low level of coupling. But this cohesion, how do we judge the level of cohesion? Okay, we use this formula over here. Okay, basically it's n multiplied by n minus 1. All right. And this basically, this calculation is the maximum number of possible couplings. So if I have a class A and I have a class B, okay, the maximum number of relationships that can exist is one going this way and one going that way. So it's 2. Okay, another one going this way doesn't really count. It's still 2. All right. Had I had the A and the B, and I have 2 arrows going this way, still that counts as 1, because we're looking at the general direction from A to B and the general direction from B to 1. Okay, and now we look at the number of classes in my package that actually do have coupling. I divide it by the n multiplied by n minus 1, and that gives me a ratio of how many relationships actually exist from those that could have maximum possibly could have existed. Okay, and I end up with a ratio of 0 to 1. 0 means basically I have no cohesion. Okay, so if this is my max number of couplings or relationships within classes, and this is the actual number of relationships. So if this is so small, the actual is so small, and divided by anything is going to give me a 0, that means that really my classes are completely disconnected from each other. If the number over here is very high, it can only reach the maximum, but so it's so high that it's actually reached the maximum, then the result of this calculation would be a 1. 1 means we've reached the maximum cohesion. Let's take a look at an example of this. All right, so first off, this is the maximum coupling. How do I recognize it? It's n multiplied by n minus 1. So what's n? N is the number of classes. So we got 1, 2, 3, 4, 5. Okay, so that's my 5. That's n multiplied by n minus 1. So 5 multiplied by 4. All right. And now comes to the counting of the actual relationship. We have 6. How is it? So this is 1. This is 2. Okay, so let me just write this again. 1 and a 2. This over here is bidirectional. Okay, so this is actually 3 and 4. This is unidirectional, only an arrow on one side. So this is a 5. And same thing with aggregation. It's also unidirectional, and that's 6. Okay, and this is why we have 6 divided by 5 multiplied by 4 gives me a 0.3. Now, again, remember, it's all about interpretation. What does 0.3 mean? Is it good? Is it bad? We know that 1 is pretty good. And we know that 0 is pretty bad. But what does 0.3 mean? We don't actually really know. Okay. Do we actually want to reach a 1? Well, we don't want to force the issue either. We don't want to force the issue either. So we got to be like careful about our interpretation of these numbers. All right. Now at the class level, okay, so far what we'll be looking at is the package level. But at the class level, there is also a number of metrics that we're going to look at. Okay. So the first of which is called the weighted methods per class. If I have a class over here, okay, got to go class X. There is different method, F1, F2, F3. I use something called the weighted method. So for each one of those, I give it a number. And this number is a calculation of this complexity. The actual calculation of complexity is not part of this course, it is not part of this metric. There's a number of ways I can create or calculate a complexity of a method, and I come up with a number. Let's just say, for example, here's 5, something more complex here, 10, something that's very trivial here is a 1. So the total WMC is 16. All right. Now, what does the 16 tells me? It tells me how complex this class is that I'm dealing with. Okay. So classes that have a total WMC that is small, then that means it's a very trivial class, which means I can understand it easier, I can maintain it easier, I can extend it, I can reuse it much, much easier. All right. Theoretically, this metric means if I have one function and it has a WMC of 1, so it gives me a total of 1,000. If I have a class that has 1,000 functions, each one of them is 1, 1, 1, 1, that still gives me a total of 1,000. So that means a class with one function that is very complex, that it gets a WMC score on by itself is of 1,000, is similar to a class that has 1,000 simple functions. Okay, so each function by itself is simple, but when you're considering all 1,000 at the same time, it does make the class quite complex. Right. Next up is the depth of inheritance tree. It's very simple. Right. So if I have a class, if I don't have any ancestors above it, then it has a depth of 0. If I have something above it, then it has a depth of 1. The thing that is above it has a depth of 0. Okay. If it has something below, that thing that is below has a depth of 2. The deeper we go, the harder it is to understand the class. Okay. If I have a variable called X over here, and I'm inheriting it from the above, I don't know if it was defined over here. Oh, sorry. I don't know if I print it, am I getting the one from this class over here, or am I getting the one from this class over here? Okay. Imagine something that has a depth, a DIT of 50, means there's 50 classes above it, right? And I print a variable y. I have no idea where to get that y from, right? Similarly, the same idea applies to overriding functions. Okay, so if I inherit a function and I use it, I'm not really actually sure which one of those 50 classes that are above me that I'm actually inheriting this from. Okay, not because I saw it in one of the classes means this is the one that I'm going to be using, because it might have been overridden by one of the middle classes in my ancestry. The next one is called the number of children, and this is the number of immediate children. Okay, for example, the NOC of this class over here is 4. You got 1, 2, 3, 4. And basically what this metric is describing to us is that if I have something that has a lot of children, that means all of those ones they need something from the parent class. It makes this one more rigid, more less likely to change, more less likely to be removed, because there's just so many dependents on it. All right. And if I have a class as such and it has a very high NOC, and I have, here's my class, I'd rather point to this one over here, because I know I'm pointing at something that is stable, that's not going to be changing anytime soon. Okay. A fourth metric is called the coupling between objects. This is a very, very simple one. Now, this is not talking about actual classes, but rather an object. So I'm going to draw it as a circle over here, because an object, for example, object A, could be connected with another object A. So another object of its same type, right? And the coupling between objects is basically the number of objects that I'm connected with, whether it's of the same type or a different type. Okay, and the whole point about this is that if I wanted to take this object over here in the middle, I gotta drag along with it a number of other objects, 1, 2, 3, 4, 5, 6. Okay, because there's strings. Okay, that really tells me my level of reusability of this object in the middle. Okay, if something has a high level of coupling between objects, okay, makes its reusability a lot less. Okay, because you're gonna take 50 other things that maybe you don't need. If I have an object that has a CBO that is very low, that makes it a prime candidate for reusability. Because if I take it, then I don't have to take anything else with it. Maybe I take one other object with it as well. Okay, so these are all very, very simple metrics. One other one is called the response for a class. So let's just say I have a class over here. I have different functions. Okay, and I get a method call from something that's outside, another class. All right. The response means how many of these functions did I actually execute as a response to this call over here. So one scenario is I might end up calling a class, calling a function over here, and then it executes without calling any other function. Okay. Whereas I might call this function over here, f1, calls f2, calls f3, calls f4 before it does all the return. So my RFC for the top one is a 4. My RFC for the bottom one is a 1. In general, that does tell me a whole bunch of things. Okay. First of all, how cohesive this class is. And we're going to get to that in a moment. Okay. You do want the relationships in the middle to be, highly dependent on each other. But maybe you don't actually want it so much because it does raise the complexity of that class. A classical example of this, if you take a look at the stack class, so there's a pop, there's a push, and there's an is empty. They rarely talk to it, they never talk to each other. The pop doesn't talk to the push, doesn't talk to the is empty. Which means that if I wanted to use this class called stack, I know its use is easy because I use one of those classes, one of those functions, and I know it's not going to be connected to each other. So I just have to look at that one function, understand what it needs, understand what it does, and that's it. Now, if I'm calling on a function in a class, f1 is going to then call f2, f2 calls f3, f3 calls f4, f4 calls f50, comes back to f2, and so on and so forth. That means that when I'm looking inside and I want to understand what is actually happening in response to my function call, it then becomes quite a bit complicated. All right. The last metric that we're going to look at in this chapter is called the LCOM chapter. Sorry, the LCOM metric. And LCOM means lack of cohesion. Okay, so just like in a package, we want classes to be cohesive. All right. And a lack of cohesion would be a bad thing. All right. Within a class, we also want our classes to be cohesive, so the functions to be cohesive. All right. We don't tend to want to have functions that are not related with each other. Okay. Now, if you look at something like that stack class that I just explained a moment ago, naturally the pop is not going to actually be dealing with the push. However, they are actually in an indirect way dealing with each other, because both of them are interacting with the same data structure. So although ostensibly they look like they are completely disconnected and they should belong in different classes, they actually rightfully belong in the one single class called stack, because they are actually quite related to each other because they're dealing with the same data structure. All right. Now, a lack of cohesion is a metric that we're going to be computing. We're going to get a minimum of 0. And then the higher the number, we can go as high as we can. Now, when we get a 0, that means there's a 0 lack of cohesion. You need to be able to read this as a negative negative. A 0 lack of cohesion means that there's actually high cohesion. So a 0 lacking of cohesion is actually a good thing. All right. Whereas if I have a high number, let's just say 100, so I have 100 of that lacking of the cohesion, that's not a good thing. Okay. Now let's take a look at how we actually compute this. All right. Remember, I was talking about the stack class just a moment ago. Right? We said that the push and the pop, despite them not actually calling each other directly, but they're actually quite related because both of them are dealing with the actual stack. Okay. We're going to look at something very similar here when it comes to the data structure, but we're going to look at it. We're going to replace this with variables. So I have M1, M2, and M3. M1, M2, and M3. Okay. So M1 says, I'm using variables A, B, C, D, and E. M2 says I'm using variables A, B, and so no. Yeah, A, B, and E. All right. And then finally I have M3 is using variables X, Y, and Z. What I do is I look at the methods that do share variables. All right. And I subtract that from the ones that don't have variables being shared with a minimum of 0, meaning if I have really 0 lack of cohesion, then this is the best case scenario. All right. So M1 and M2. So let's just say, let's talk about lacking here and non-lacking. Okay. Or let's just say an empty null intersection means there is no variables being shared, and a non-empty intersection is the ones that have something shared. Okay, so here let's just actually call it something different. Let's call it not sharing to make it simple, minus the sharing. Okay, and we have to take each different combination. Okay, so M1 and M2, they're sharing. I put down 1 over here. M1 and M3 not sharing, put down 1 over here. M2 and M3 not sharing, I put down over here. Okay, so it's 2 minus 1. That gives me an LOC of 1. Okay, so I'm not doing so bad, but I'm not doing so good either. I mean, you can see there's a disconnect between M2 and M3 and M1 and M3. So those together are very cohesive, yet this on its own is isolated. In other words, this over here, M3, might as well could have belonged into a different class. Okay, let's take a look at different examples over here. All right, so this is the one we've just computed. Now let's take a look at this example. All right, and I say let's put it down. What did we say over here? Not sharing minus the sharing. Minus the sharing. So M1 and M2 Sharing, yes. M1 and M3, they'll be not sharing. Finally, M2 and M3, they're sharing. So it's a 1 minus a 2. But for a minimum, this should be -1. But for a minimum of 0, so then I will say that the LCOM is 0. Okay. So despite M1 and M2 over here, not actually sharing any variables with each other, still in general, this class and its method have a high level of cohesion, or in other words, they have a 0 level of a lack of cohesion. All right. So is this clear for everyone? Let me just pause this here for a second. All right. The LCOM, guys, was it clear for everyone? So I hope it is. And in an exam, I would basically get you the functions, the variables, what functions are using which variables. Then you'll be able to figure out which ones are which ones what was I say? Which ones are sharing variables and which ones are not. Okay, here's another trick just before I let go of you of this. Remember the slide over here. Remember that I can actually have a class that's actually associated with itself. That doesn't count. We're looking for cohesion, as in people in the house talking to each other, not people in the house talking to themselves. So if D is self-associated with itself, this doesn't count in my calculation. It still comes as a 0.3. And these are the only two things that you should watch out for in an exam question, right? Other than that, so that would be it for this lecture. Let me just pause the recording here for a second, or even stop.